Hello again. In this example, we are going to see a problem of analyzing a circuit and doing a redesign with a different set of devices. So in our problem, we have a circuit. We already know the structure of the circuit. This comes from an alarm system, but we don't really know what the alarm does, and this circuit is broken. Some devices has been burnt out. It doesn't work, but we know the structure after taking a look at the circuit board or whatever. So we know that the A input is connected to the system activation switch. B comes from a fire sensor. C comes from a sensor at the front door of the house, and D comes from a presence sensor in the main area of the house. Okay, and we know that all these inputs are activated with a 1. They are active high input signals, and the circuit thus considers all these input signals and generate the signal to ring the alarm if necessary, and the alarm is supposed to be activated when Z is equal to 1. Okay, but we don't really know in which conditions the alarm actually is activated or not. So we first need to obtain the function done by the circuit. And maybe the good thing is to obtain the truth table or kernel map or something. And once we have the table, we can try to describe how the alarm actually works. Okay. Then, because the circuit is broken, we are asked to build a new circuit with the same functionality by using only NOR gates. So to analyze the circuit, analyzing is going to the opposite path that we follow when designing a circuit. So if we have the circuit schematic like here, the idea is that I go from this circuit and I obtain the expression for the output. And from the expression, I hopefully can obtain a table representation, either a K-map. Maybe it's easier to go first to the K-map and then to a truth table. So in the truth table, I have all the information. I will have all the information on how the output activates, in which conditions, and so on. And from the truth table, it should be easier to give a verbal description of what the circuit does. Okay. So it's the design process, but done in the opposite way. Actually, the analysis is easier because the circuit is already done. We don't have to take any decision, just do the calculations. So to obtain the expression, it's done because we know the expression calculated by each gate. For example, this is a NAND gate. The inputs are A and C. So at the output, I will have A and C complemented because this is an AND. Here it's an inverter, so the input is P, the output will be B complemented. Here it's another NAND gate. I'll have A and B complemented, and Z will make the AND of all these terms and then complement the result. So the expression for Z will be AC complemented and B complemented and AD complemented and all these complemented. Okay, so this is one AND, the inverter, the other NAND, and this is done by the final NAND gate. So to move this expression to a kernel map and to a truth table, we have seen in other examples the best option, the easiest option is to write it as a normalized expression, as a sum of products or as a product of sums. It's easy to do if we simply do the complements. Okay, the complement, I eliminate the complements by applying the Morgan theorem. So the complement of the first part is AC complemented twice. The N becomes an OR. Then I have B complemented twice, another OR, and I have AD complemented twice. I don't eliminate the first complement because now all those double complements will give AC plus B plus AD, and now it's a sum of products. Okay. We have already seen how we can go from an expression like this to the Karnaugh map or directly to a truth table. We can find the verbal description either from the truth table or the Karnaugh map. Okay, it depends on your preferences. Because the problem says obtain the truth table, I will go directly from this to the truth table. So we will draw a truth table here. We have A, B, C, and D, and I have Z here, and I will write all the values. 0, 0, 0, 0, 0, 0, 1, 0. You can skip this part of the video and do a fast forward if you prefer. It's not going to work like that. I have to write in a more compact way. So let's try like 0, 0, 0, 0, 1, 1, 0. That's why I normally prefer Karnaugh maps, because it's a more compact representation. Oh, I already made another mistake here. Fortunately, I can move it here. 0, 0, 1, 1, 3, 4, 5, 6, 7, 1, 0, 0, 0. One, 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 0, 1, 1, 1, 1. And okay, now let's arrange it so that it fits in our given space. Okay, or less. And now the output in each case is, the output is 1 whenever A and C are 1, both of them. So I find these cases, A and C both 1 is in this case here, A and C, this case and this case. Now the output is 1 also when B is 1. Okay, so anytime B is 1, this is here, 2, 3, 4 cases, and this is in all these cases here. The output is also 1. Okay, and now it's also 1 when A and D are 1. So A and D is in this case already considered, all the rest are already considered. So I have these cases left when the output is 0. I hope it's okay. 1, 2, 3. Okay, so now that's the truth table. From the truth table, I can try to find a verbal description of what my circuit does. Okay, so remember that A is the alarm connection switch. So from here can divide the map. This here the alarm is off, disconnected, and here the alarm is on. Okay, so we'll first try to check what happened when the alarm is off and when the alarm is on. And from this part here, we see that when the alarm is off, the alarm will not ring except when B is equal to 1. Okay, let's put them a bit closer. Okay, so they are easier to identify. So I can express like that. Okay, if alarm is off, it means A equal to 0. Okay, only activates if B is 1, and B is the signal coming from the fire detector, so it only activates if fire. Okay, mean B is 1, which is quite good, because even if I have disconnected the alarm, I want it to ring if there's a fire, because this is very risky operation. Actually, this is how real alarm systems work. You can deactivate your alarm, but there are some sensors like the fire sensor, smoke sensor, CO2 gas sensor, and all these sensors that detect something risky for the life will make the alarm to ring. Okay, now but if the alarm is on, now A equal to 1, I have this part here. And in this case, if the alarm is on, I see that the alarm will ring in almost any condition. So it will ring whenever I remember C is the door detector, D is the presence detector. So if the alarm detects anything, presence, door opening, or fire as well, the alarm will ring. The alarm will not ring only when there's no emergency condition. When the door is closed, there's no presence, and there's no fire. This is the normal state when I leave home. I connect the alarm, there's nothing strange, so the alarm is deactivated. Okay, if there's any condition in any sensor, it will ring. So when the alarm is on, then what happens is that ring in any sensor activation. Okay, which means fire or presence or door. So as it is supposed to happen when I leave the house. Okay, so this will be my verbal description of my system. Now we have it very clear what the alarm really does. Okay, and we can be safe that if we leave the house, we deactivate the alarm, or if we arrive to the house and we deactivate the alarm, we can be safe that if there's a fire, it will ring. Okay, and if you leave the house, this actually works as expected. It will ring the alarm in any strange condition. Okay, but now the problem is that our circuit is broken. Okay, maybe some of these gates has got broken. Okay, they don't work anymore, but it may be because it happened that I have some chips with NOR gates, or because I have some access to technology with NOR gates or whatever. We want to build a circuit that does the job, but doesn't but can be that, but we want to do it only with NOR gates. Okay, so we'll do a little bit of planning, and I want to do it in a single page. Okay, so we'll move it here a little bit. Okay, and then we will move all these a bit up. Okay, so the next step, sorry, here, okay. Our next step could be to redesign this function, but using only NOR gates. So it's because it's NOR gates, what we know is we are going to do a circuit with two levels, NOR and NOR circuit. Okay, first NOR level, second NOR level, which is equivalent to a NOR AND circuit. Okay, or AND comes from a product of sums expression. Okay, so we are going to do a Karnaugh map for our circuit. Let's do it like this, make it square like this, more or less. Okay, we are going to do a Karnaugh map for our circuit, and from the Karnaugh map we will derive a minimal product of sum, and from the product of sums we could write directly an OR AND, or as in this case a NOR circuit. So I have AB, CD, 1, 0. Now, first thing is to move all the information from the truth table to the Karnaugh map. Because we have used this sorting, it's important to keep the same sorting. Now I can go through the minterms in order 0, 1, 2, 3, 4, 5, 6, 7, and then copy all the data from here. So data is 0, 0, 0, 0, 0, 0, 0, 0. Note that I'm writing in the map in the order that I follow in the table. Now it's 1, 1, 1, 1, 1, 1, 1, 1. Sorry. Now it's 0, 1, 1, 1, 0, 1, 1, 1. The last one is 1, 1, 1, 1. Lots of minterms here. Okay? But because it's a product of sums, I have to go and use the max terms to find my implicants. It's very simple actually. If I start with this 0, I have a first order implicant here, another first order implicant here, which is next to the other one. So this will be a second order prime implicant. Now this 0 together with this 0 makes another first order prime implicant, and that's it. The expression for my function would be z equal to this would be a plus b and this term is a complemented. No, a doesn't appear because it's either 0 or 1, so it will be b plus c plus d. Okay, there are no inverters. This is my expression. So this circuit I can do it like this with OR AND, or directly with NOR. If you want, you can convert this to the NOR expression by doing the double complementing the expression. Okay, so I complement this one and this will be A plus B complemented, which is a NOR. And then I have the other one. This is one NOR gate, B plus C plus D complemented, which is another NOR gate, and this N becomes a NOR complemented, which is the third NOR gate. Okay, but if you if you have had some training, you must know that from the product of sums I can go directly to a NOR structure. So my circuit will have one NOR for the first term, another NOR gate for the second term, and another NOR gate for the output. The first term is A or B. The next term is B or C or D. And this is it. Okay, so that's it. I just find the chips or the technology with the NOR gates. I put together this circuit, and this will make exactly the same operation. Okay, I will move it here. This circuit is a perfect substitution for the original one. Okay, I can put this in place of the other because they implement the same function. That's all. Thank you.